Hello and welcome to the very second episode of the Science of Math discussion. Today it'll be my first mathematical episode where I'll be talking about e to the power of x and how the derivative of this is still e to the power of x, which is something I've been introduced to recently and I found quite weird. Before I get in, if you'd like to leave any recommendations for future episodes in the comments on YouTube, or feel free to subscribe or follow on Spotify, on YouTube, or any other place where you listen to these podcasts. Okay, so before I get into what e to the power of x means and how we're going to derive this, I thought I'd give a quick introduction to e. I'm not going to do it a very, very in-depth one because maybe e could be a future episode, but I'll give you a quick idea. E is a constant, roughly equal to 2.71828, and with infinite decimal places after that. It's referred to as Euler's number, spelled E-U-L-E-R. I'd read this Euler, but apparently it's pronounced Euler for after the person who discovered it. E is irrational. It cannot be written as a simple fraction. This can be proven by a quick method, which I might do a future episode on. E turns up everywhere in both maths and physics, and it's very, very common, and it's not quite as used as much as pi, but it is one of those numbers which you'll become very familiar with the more you do maths and physics. You can see it. I found a list of the main things it's used in: logarithms, compound interest, probabilities, and the behavior of quantum particles. These are just the main ones, but there are quite a few other ones. Okay, so e to the x. If you want to think of a graph of e to the x where the x-axis goes along in increasing x and the y goes up in e to the x, so as x values go up, e to the x, the power of e is x value. That kind of makes sense. The graph is an exponential function, so it's going to increase in gradient. It sort of curves up faster and faster. One quick thing about this e to the x graph that is quite cool is that the area up to any value of x is just e to the x, which is a weird property of this graph, and it makes it quite simple to find the area. Okay, so the point of this episode, and this is a cool little mathematical proof of finding that the derivation of e to the x is still e to the x. Now, the method I'm about to show you is a little bit abbreviated, it's a little bit quicker. I'd recommend to go see the Khan Academy version of this. It's a full one. It's a good 9-minute video, and it's really impressive to watch. Okay, but here is a quick way. So to be able to understand how this works, you have to know a basic understanding of the gradient function. That is dy over dx, the change in y over change in x, and then you can find this. It'll be a short function which you can enter any value of x to find the gradient at that point. Now this is how we figure out the derivation, because this is the first derivative. So this change in y over change in x is how we work it. So I want you to imagine 2 points on the graph. The first one is the origin, the x, and then the y value is e to the x. This is just a standard point. And then the point further along the graph, further along in the values of x, where it's x plus h and e x plus h. Therefore, the change in x, the increase in x you've had, is h. So if you want to add that to the dy over dx, the first derivative, the gradient function, so the change in y will be the e x plus h minus e to the x, because this is the second higher value of the y minus the first value, so this would be the change, and then the change in x is just h. Now we can simplify this by e to the x plus h could also be written as e to the x times e to the h, because if you times two things, their indices add, and then you keep it as minus e to the x, so therefore we can write it as e to the x times e to the h minus e to the x goes to over h. Sorry. Then you can factorize into e to the x, and then open brackets e to the h minus 1. This is just an easy way of this will be useful all over h. Okay, so now here is when we start to think about it as the derivative becoming just e to the x. So inside the brackets you have e to the h minus 1. Now we write lim h to 0. This means as h becomes 0. Now, as h becomes 0, we have e to the h minus 1. As h becomes 0, this will become e to the e to the 0, but slightly more than 0, minus 1. This we can basically sort of write it as 1 plus minus 1, because anything e to the power of 0, or anything to the power of 0, is 1. So it'll be slightly more than 1, because it never quite becomes 0, but slightly more than 1, minus 1. Now this can cancel with h to leave us with just ex over h. Now this is because as h becomes very close to 0, so will eh minus 1. They'll both become very close to 0, so therefore you can just cancel them both. Now this is a bit of a... It's correct, but it's just not quite the nicest way of doing it. Which here is a fuller version, as I mentioned, on the Khan Academy website, by the way, which I find is an amazing place to find those. So, to summarize, to find the derivative of e to the x is just e to the x, you're going to want to try and write out dy over dx. Now you can do this by making the change in x, the increase in x, h, so therefore you can write out what dy over dx would be. You're going to simplify this, factorize this, and work it out as h becomes 0. What effect would this have on our first derivative or gradient function? And you'll find that all that's left is ex over 1. The way of writing the h becomes 0, it's a small notation thing. It'll be lim for limit, and then h to 0. As h becomes 0, you'll find it just cancels, and you're left with ex over e to the power of x over 1. This is an abbreviated version, of course. If you're watching this on YouTube, it'll be far simpler to follow because there's a photo currently on screen explaining this. If you're on Spotify, feel free to jump on YouTube if you don't understand, but I hope I've done my best to try and explain this out loud. If you find it a bit unclear, please let me know exactly where in the comments, and I'll try and help you. And as I said, I'm not exactly an expert in this, so feel free to correct me in the comments. Okay, that's all for today's episode. Hopefully next week I might have my very first episode with a guest, so that'll be a bit more exciting, a bit more fun to listen to, I'm sure. And see you next time.